Okay, guys. I wanted to go through a few things with you. You should have already watched the video over titration of an unknown acid. Unfortunately, oh yeah, remember to make sure that you have watched that video if you haven't yet, and there are questions embedded with the video. The video will actually stop, pose a question, you will answer the question, and then go on. And you will get a grade in Infinite Campus for answering questions on that video. So please don't forget to do that if you haven't done it yet. Um, I wanted you to see that video. I wanted you to see the process of a titration because, again, this is something that we would have spent quite a bit of time doing in class. We would have probably done at least a couple of labs where you did those titrations, if not more. So I really hate it that you guys are missing out on that, but I wanted you to at least see the procedure, learn a little bit about the equipment and how it would work and what it's used for. So we're going to review over that just a little bit again here in a minute, but before we do that, I wanted to go over some dilution calculations. We did a few dilution calculations when we talked about solution chemistry. And now looking at acids and bases, we're going to go back and look at those again. Again, we want to do dilutions when we have a concentrated acid or base or any solution that's more concentrated, and we want to make a certain volume of a less concentrated solution. So when we're looking at acids and bases, we have to look at chemical equivalents. A chemical equivalent is the amount of solutes that have equivalent combining capacities in a neutralization reaction. So when we're looking at acid and base neutralization reactions, we know that the hydrogen ions and hydroxide ions come together to give us water. So they cancel out, the acid and base cancel out to give us something neutral. Remember, hydrogen ion is acid, hydroxide ion is base. So when hydrogen and hydroxide combine, they form water, which is neutral. So that's a neutralization reaction. And so we know that the equivalents are the number of hydrogen ions and the number of hydroxide ions that the acid and base has. If the acid has 2 hydrogen ions in it, but the base only has 1 hydroxide ion, then those are not going to be chemical equivalents, meaning that they are not going to cancel each other out because you have 2 hydrogen ions and only 1 hydroxide ion. So, we have to look at the chemical equivalents in terms of hydrogen ions and hydroxide ions because these are the ones that these equivalents are going to cancel one another out. So the equivalent mass of an acid is the mass of acid in grams that will produce 1 mole of protons. So when we're talking about the number of equivalents, because that's the main thing we're going to be talking about, we're not going to really be talking about the mass, but we're going to be talking about the number of equivalents. Essentially, when we look at the number of equivalents an acid has, we're essentially looking at the number of hydrogen ions in the formula for the acid. So, for example, HCl has 1 equivalent. It has 1 hydrogen ion. H2SO4 has 2 equivalents. It has 2 hydrogen ions. H3PO4 has 3 equivalents, meaning it has 3 hydrogen ions. So again, to find the number of equivalents for an acid, you just look at the number of hydrogen ions that it has. Again, you could look at mass with this as well, but we're not going to be doing that. When we look at the equivalent mass of a base, it is the mass of base in grams that will react with 1 mole of hydrogen ions or provide 1 mole of hydroxide ions. And so essentially, we're looking at, well, the number of hydrogen ions that it can react with depends upon how many hydroxide ions there are. So essentially, we're looking at the number of hydroxide ions in the formula for the base. So if we're looking at, for example, NaOH, well, NaOH has 1 OH, 1 hydroxide, so it has 1 equivalent. BaOH2, well, it has 2 hydroxide ions, so it has 2 equivalents. AlOH3 has 3 hydroxide ions, so it has 3 equivalents. So in the formulas that we're going to be using when we talk about the number of equivalents, we're talking about the number of hydrogens if we're talking about an acid, or the number of hydroxides if we're talking about the base. And so that's the main thing that I wanted you to get from this. So when we look at solution concentrations, we know we've already learned several ways we can express solution concentration. We've looked at percent by mass, we have looked at molality, and we've also looked at molarity. So another thing that we can look at is normality. The normality is the number of equivalents of an acid or base, so the number of equivalents of hydroxide ions or hydrogen ions, times the number of moles over the number of liters. So essentially, normality is the number of equivalents, which we are expressing as letter N. Again, that's the number of hydrogens or hydroxides, times the molarity. Remember, molarity is moles over liters. So when we take this equation for normality, the number of equivalents is N, moles over liters, that's molarity. So the equation that we can use to kind of relate normality and molarity together is normality big N, is equal to little n equivalence times molarity. So that is something that we want to remember. And again, we can't do these practice problems in the textbook because I don't have the textbook here at home with me. So we're going to look at some other practice problems. So again, as I was speaking of earlier, we can use normality or molarity when we're doing calculations to determine when we're talking about making a dilution, making a dilute solution from a more concentrated solution. So it doesn't matter if we're using normality or molarity, the equation is the same. You're going to take the normality or the molarity times the volume for the first solution and set that equal to the normality or the molarity times the volume of the second solution. The thing that we need to remember here, there's a couple of things that we need to remember. First of all, if we're going to use normality, then both solution concentrations have to be in normality. If we're going to use molarity, then both solution concentrations must be in molarity. The other thing we need to remember is whatever volume we're using, we have to use the same volume on both sides. So for example, if we're using milliliters, that's perfectly fine as long as volume 1 and volume 2 is in milliliters. The same is true for any other volume. If you're using liters, volume 1 and volume 2 must be in liters. So again, your solution concentrations have to be the same concentration unit, and the volumes have to be the same unit as well. Other than that, the equation is the same, and so that's how you're going to work these problems. So what I wanted us to do first is I wanted us to work out some equations where we're just talking about doing dilutions, and then we'll bring normality and molarity into it. So again, remember it's N1V1 or M1V1 equals N2V2 or M2V2. Okay. So first thing then that I wanted to do is we were going to look at just a couple of problems from quizzes. These are just some problems from quizzes that I found. And I'm also going to work these out on my iPad as well. So let me get my program open here real quick for you, because it doesn't do me any good to open it until I get ready to use it, because it goes to sleep on me. And I know there's a way that I can fix that, but in any case. Okay, so let me open this up on my computer here really quickly before I do anything. Show the QR code. Scan the QR code to connect it to my computer. And then I'm going to screen mirror my computer. Let's get rid of this. And then let me go to my paper app here. And I forgot to get anything to write with, but in any case, I think I can make it work. All right. So here we go. All right. So our first problem, so let's go back here and look at our first problem first. We have 10.8, and just let me go ahead and just move this over. We have 10.8 milliliters. And if you hear a cat meowing, it is my cat. She is being silly. She's been doing this all day. Okay, so we have 10.8 molarity HCl. We want to know how many milliliters of this 10.8 molarity HCl are required to make 100 milliliters of 3 molar HCl acid. Okay, so here we're using molarity and milliliters. So we're going to use our formula M1V1 equals M2V2 since we're using molarity. Okay, and so let's just go ahead and say that this first molarity here is our solution 1. So we want to know how many milliliters. So we want to know the volume, so that's our X. And the molarity of this first solution, how many milliliters, which is our X, of 10.8 molar, so 10.8. And again, that is molar. Let me try to write this a little bit better here so that I can put my unit in. Okay, is equal to, and someone's supposed to be my son. Okay, the second solution is 100 milliliters of 3.00 molar. So 3.00 molar times 100 milliliters. Okay, so now we've got to solve for X. Well, I hope you can see that in order to solve for X, we're going to have to divide both sides by the 10.8 molar. Okay, so 10.8 molar cancels out. And we have X is equal to 3 molar times 100 milliliters divided by 10.8 molar. Again, the molars will cancel out and our unit will be in milliliters. So then I'm going to use my Scientific Web Calculator 2.0 to do this calculation. Again, the main thing you have to remember about this calculator is to make sure that you push clear before you start. So again, our calculation is going to be 3.00, which I'm just going to type in 3, times 100. And I'm going to go ahead and push equals. And that gives me 300. And then I'm going to divide that by 10.8. 10.8. And just kind of, as you're punching that in, look at the screen and make sure that it's typing in what you expect it to. Because if it doesn't, then you know you're not going to get a correct answer. So what we're getting here then is we're getting 27.77777. Okay, so let's look at our problem. It looks like the least number of significant digits was 3, so that means we need to give our answer to 3 significant digits. So 27.77 will round to 27.8. So 27.8 milliliters will be our answer. So that's what I've written here, 27.8. So let's go see if we're correct. It looks like our answer should be this first one here, and that is correct. Okay, so let's go ahead and look at another one then. Let me go ahead and clear all this. And this one is, what volume of 1.50 molar KBr can be made from 15.6 milliliters of concentrated KBr with a molarity of 9.65 molar. Okay, again, we're using molarity and volume here, so I'm going to go back and write my formula. M1 V1 equals M2 V2. Sorry, I'm getting all excited here. M2 V2. And here, what volume, so again, our volume is going to be our X, and we're just going to go ahead and say that this is our solution 1, can be made from 15.6, what volume of 1.50 molar KBr? So our molarity for that one is 1.50 molar. Can be made from 15.6 milliliters, okay, that is a volume, 15.6 milliliters with a molarity of 9.65 molar, so 9.65 molar. Again, we're going to solve for X, so we're going to have to divide both sides by the 1.50 molar. Okay, this cancels out, and on this side we have X. Over here, we're going to have 9.65 times 15.6 divided by 1.50. So I'm going to go back to my Web Calc 2.0. And I'm going to clear, and I'm going to type in 9.65. See how it did? 9.65 times 15.6. 15.6 equals, and then I'm going to divide by 1.50, which I'm just going to say 1.5. And that's giving me 100.36. If we go back and look at our problem, it looks like we need the least number of significant digits is 3. So 100.3 rounds to 100. But again, we need 3 significant digits, so we're going to have to make sure that we put that decimal there at the end. With that, remember that any zeros at the end of a number with a decimal are significant. So 100 with a decimal has 3 significant digits. The molarity cancels out, and our unit is milliliters. So 100 with a decimal, milliliters. So that looks like this should be our correct answer. Let's check. Yes, we are correct. Okay, I think there is one more problem here that we can do, or maybe not. That one's not got molarity and volume. Let me see if there's any more. Nope. No. All these have grams in them. Okay, so that will be it for that quiz that I wanted us to practice. Okay, the next thing I wanted us to look at was titration. But before we do that, I wanted us to look at a couple of more review problems. And these are going to be some review that I have on an old test review. Okay, same thing here. We're doing dilutions. the difference is we're going to use more than just molarity now. We're going to use normality as well. Remember the formula where whether you're using normality or molarity is the same. The only thing we need to make sure is that both concentrations have to be in normality or molarity, one or the other, and both volumes have to be the same, either milliliters or liters or whatever. Okay, so let's look at this number 5 here. How many milliliters of 1.30 normal H2SO4 solution would be needed to prepare 400 milliliters of a 0.750 normal H2SO4 solution? So again, we're doing an H2SO4 solution, and what we're going to do is we're going to use a more concentrated solution here, the 1.30 normal, to make a more dilute or less concentrated solution, the 0.750 normal. So again, how many milliliters? So we know that's our X. So let's go back over here to our paper. And again, since we're using normality here, we're going to use the N1 V1 equals N2 V2. Okay, so again, let's say that this first one is our solution 1. How many milliliters? So that is our first volume of 1.30 normal. So let me go ahead and erase that and make myself a little bit more room here. So X, and it is 1.30 normal. And then how many milliliters of this 1.30 normal would be needed to prepare 400 milliliters? So that's going to be our second volume, 400 mils, of a 0.750 normal solution. So 0.750 normal. Okay, so again, we're solving for X. So we're going to have to divide both sides by the 1.30 normal. Notice that if we have molarity or normality on both sides, then they cancel out. If we don't have that on both sides, then they can't cancel out, and they have to be able to cancel out. So that's why we need to have either normality on both sides or molarity on both sides. The same is true for the volume. Whatever volume we have on one side, we must have on the other so that they can cancel out. So again, here on this side, 1.30 normal cancels out, and we have X. On the other side, the normality cancels out, and we have 0.750 times 400 divided by 1.30. So let's go to our web calculator and make sure we push clear, and 0.750, I'm just going to type 0.75, times 400 equals, then divided by 1.30 equals, okay? And if we go back and look at our problem, it looks like our least number of significant digits looks like it's right here with 1, but I'm going to go ahead and put a decimal there because I don't like my answer having just one significant digit. So with that decimal there, all of these zeros are significant because they are zeros at the end of a number with a decimal. So that means all of these numbers have 3 significant digits, so we need to round our answer to 3 significant digits. So 230.7 rounds to 231. So my final answer here would be 231, and then again my unit is milliliters because that's the only thing that didn't cancel out. So that would be my answer for that problem. Okay, let's look at one more, and I'm having you to do these because you're going to have to do something similar to these on your test that you're going to be working on Thursday and Friday. So that's the reason why that I'm going over this with you, because I want to be sure that you can do this on your test. Okay, so one more dilution problem before we go on to titration. What volume of 0.250 normal H3PO4 would be required to prepare 1.75 liters of a 0.200 molar H3PO4 solution? So as you can see here, guys, we have a normality and we have a molarity, and we cannot use that. We're either going to have to convert the normality to molarity, or we're going to have to convert the molarity to normality. Okay, one or the other. So then what we're going to need to do is we're going to need to use our equation. Remember that normality is equal to equivalence times molarity. So let's just go ahead and take our molarity and convert it to normality. Okay, so our number of equivalents in H3PO4 is going to be how many? Okay, I hope you said 3. 3 hydrogen ions means 3 equivalents. So our N is 3. Okay, and then our molarity is 0.200. So times 0.200 molar. So when you do 3 times 0.2, and again you can punch that in, but 3 times 0.2 should be 0.6 if I'm thinking correctly, but we'll go ahead and do it. 3 times 0.2 should be 0.6, and that is correct. So then our normality is 0.600. And let me see here, because I don't know that this problem will work out, because we can't take a molarity solution and dilute this lesser concentrated solution to make a greater concentrated solution. So what we're going to do then is we're going to say that this solution is 0.75 instead of 0.2. Okay, there we go. So what volume of 0.750 normal H3PO4 would be required to prepare 1.75 liters of 0.200 molar? And again, we just calculated that our 0.200 molar, and I'm sorry here, this is not molar. This is normal now. We have just converted by taking the equivalence times the molarity. We now have a 0.600 normal solution. Again, we could have converted that molarity to normality like we just did, or we could have converted the normality to molarity. Again, we could have substituted and I can show you how to do that as well. If we want to change the 0.750 normal to molarity, we can say, okay, 0.750 normal is equal to the equivalence times the molarity. And then to get the molarity, we're going to have to divide by the equivalence, which again, the equivalents are 3. So we're going to divide both sides by 3. And our molarity would be equal to 0.250. Okay, so we can do this as we did it. We could do normality on both sides, and we would have 0.750 normal and 0.600 normal. Or we could do molarity, and we could say, oh, this is 0.250 molar, and this is 0.200 molar. Okay, that is totally up to you as to which one you want to do. I like to use molarity better, but it really doesn't matter. We should get the same answer no matter which one we use. So let's go ahead and just do it with the normality first. So remember that our 0.200 molar is, and I'm going to just type this down here so that we don't forget it. Our 0.200 molar is equal to 0.600 normal, and that is for this H3PO4 because it has 3 equivalents. And then our 0.750 normal is equal to 0.250 molar. Okay, so, and what we'll do is we'll just try it both ways and we'll see what we get. All right, so let's go ahead and try it then with the, normality first. So if we do the normality first and we say the N1V1 is equal to N2V2. Okay, so our first, our what volume, so that's going to be our X, 0.750 normal, so 0.750 normal is equal to, okay, 1.75 liters, that is our second volume. And our normality, this is 0.200 molar, but we said that was 0.600 normal. Okay, so to solve for X, we have to divide both sides by 0.750 normal. That cancels out, and on the left we have X. On the right we're going to do 0.600 times 1.75 divided by 0.750. Okay, so clear this out. 0.600 times 1.75 equals, then divided by 0.750 equals. And our answer that we get is 1.4. Now, if we go back here and look at our significant digits, we have 3, we have 3, and we have 3. So we need 3 significant digits. We got 1.4. So for that to have 3 significant digits, we have to put 1.40. So that is 1.40. And again, our unit is liters. Okay, let's try the same calculation, but let's use molarity instead. So M1V1 equals M2V2. Okay, so again, what volume, so that is our X, of 0.750 normal, but again, we're using molarity here, so 0.750 normal is 0.250 molar, so 0.250 molar would be required to prepare 1.75 liters, so again, that's still our 1.75 liters, and then 0.200 molar is what we want to use here because we're doing molarity now, so 0.200 molar. All right, so again, we're going to solve for our x, so we have to divide both sides by 0.250 molar. The 0.250 molar cancels out, and we have x equals. And then, of course, the molarities cancel out, or the normalities cancel out. We're going to do 0.200 times 1.75 divided by 0.250. So, go back to our calculator. Clear. 0.200 times 1.75 equals, divided by 0.250 equals. And notice what we got. We got 1.4, which we're going to say 1.40 for 3 significant digits again, liters. So again, it doesn't matter whether you do the molarity or the normality, as long as you have normality on both sides or molarity on both sides, you get the same answer, 1.40 liters. So what this means is that we would need 1.40 liters of this 0.750 normal solution to make 1.75 liters of this 0.200 molar phosphoric acid solution. Okay. So that is all we're going to be doing for dilutions. Please let me know if you have any questions, and I will be happy to FaceTime you or whatever the case may be in order to help you. I'm also going to try to get all of your work that you did last week graded before it's time to actually take the test, so that you can see anything that you did incorrectly. Please make sure, you guys, it takes me quite a long time when I grade your work and I give you feedback. It takes me quite a long time to type all that feedback for you, to talk to you, to try to explain to you what you did incorrectly. So I would really appreciate it if you would take the time to read that feedback and try to understand what I'm trying to tell you that you did incorrectly, so that you won't make those same mistakes on your test. Now, you do have 2 days to take the test. The test is actually, as you can see here on Google Classroom, I have it in 2 parts. The reason for that is that the first part is quizzes. It's a quiz. And so on quizzes, I couldn't put a lot of questions where you had to show me your work. You had to do calculations and show me your work and give me an answer. And so these are all multiple choice questions. They are it's just basically recall information, and there are also some like identify conjugate acid, conjugate base, acid base in these equations, as well as there are the pH, POH, hydrogen ion, hydroxide ion concentrations that I went over for you on Monday, day 26, April the 20th, in that video in the quiz that you had to take. So those kinds of things are pretty easy to do on multiple choice questions and do on quizzes. Now, when it comes to the basic recall questions, I gave you like 60 seconds to answer those. But when it comes to the pH, POH, hydrogen ion, hydroxide ion calculation like we did on Monday, I gave you 5 minutes on those questions. So you have anywhere from 60 seconds to 5 minutes. And I think I told it to display the timer so that you can see. The basic recall question, 60 seconds should be fine. I think on the identify the acid base, conjugate acid, conjugate base, I gave you like 3 minutes. Again, those are multiple choice questions. So you have an equation, you have to tell me. It may say which one of these is the conjugate acid, and you have to pick which one. So, I thought you might need a little bit of time to look at that and figure that out. So I gave you 3 minutes on those. And then for the pH, POH, hydrogen ion, hydroxide ion calculation like we did on Monday, I gave you 5 minutes. So that gives you plenty of time to get it typed in, because I know you can't do it very fast on this Web 2.0 scientific calculator. If you have your own scientific calculator, you might be able to punch it in a little bit quicker, but I went ahead and gave you 5 minutes on that. But if you answer the question before the timer's up, then it's going to go on, but you are not going to get multiple tries to do this quizzes test part 1 like you did on the practice. On the practice, I gave you the opportunity where you could do it as many times as you wanted, because it was just practice, and I wanted you to have the initiative that if you missed things, you went back and tried it again to get them correct. But this is a test, so I'm testing that you know how to do it, and so you're only going to get 1 try on this quiz, at least at this point. If you do terribly, I might message you about doing it again. Or if you do terribly and you want to do it again, you need to email me and let me know. But when you take it, you're only going to get that 1 attempt, so please do your best. And then the test part 2 is a Google Doc. So it's going to when you click on that, it's going to make your own copy for you. You have 2 choices, just like we did on the last exam. You can You can type your answers and show, I need your answers and your work. So you can type your answers, your work, and your answers in and submit this document, or you can print this document off. You can work it out on the paper and then take pictures and upload those to this assignment on Google Classroom. And that's going to be your second part. This is going to be the calculations like what I just showed you with the normality and the molarity, as well as what the calculation that we're going to do next, which is going to be the titration calculations. So those require a little bit more work, a little bit more thought, and so rather than giving you a timed question on a quiz and then asking you to write out an answer on quizzes, I'm just having you to do that on a Google Doc, or else do it on paper and then take pictures and upload it to this assignment on Google Classroom. Also, on both of these test parts, I have put the Web 2.0 scientific calculator so that, you know, it is there for your convenience. If you have your own scientific calculator, you don't have to worry about it, but I thought that if you wanted to have it, you can have it there opened on a tab so that you can go back and forth between the test and the calculator. So the last thing we need to talk about is what the video was over that you should have already watched about the titration of an unknown acid. Basically, I just wanted to kind of review over with you the apparatus a little bit. Again, you have a ring stand, which I think we've used in class before, and then you have a burette clamp. Now, this one is a little different than the one she showed you on the video, but again, there can be different forms. But basically, your burette is this tall glass tube that is graduated, meaning it has measurement markings on it. And it is held up above your Erlenmeyer flask with the burette clamp. Now, this burette, the one she used on the video was 25 milliliter burette, but the one that we would have used, we would have actually had a 50 milliliter burette. But it's important for us to know how to read that burette. Remember that the burette at the very top starts at 0, and then it comes down, and down here at the bottom it reads 25 milliliters or 50 milliliters. It is marked off in measurements of 1 milliliter. So here we can see from 21 to 22, that is 1 milliliter, or a cubic centimeter. Remember, a cubic centimeter and a milliliter are the same amount. Notice that in between the 1 milliliter markings, which are the longer markings, we have 1/10 milliliters. So this is 21.1, 21.2, 21.3, so on and so forth. So those measurement markings give us one place past the decimal. However, we can see that this level of liquid here falls in between two of these. It falls in between the 21.3 and the 21.4. So we can estimate to the hundredths place. We can estimate to 2 places past the decimal. So again, we're looking at this level of liquid here, and notice that it is curved a little bit. That curve is called the meniscus. This happens because the water kind of, by capillary action, kind of clings, hydrogen bonding. It clings to the walls of the glass tube, and so it kind of tries to ride up, but there in the center, it doesn't have any glass to cling to, and so it's lower in the center. So we always read the level of the liquid in the burette at the lowest point of the meniscus. So when we look at the lowest point of the meniscus, we can see that it is in between the 21.3 and the 21.4. So we're estimating this as 21.35 or 21.35 milliliters or 21.35 cubic centimeters. So again, we can estimate to a second place past the decimal. The graduated cylinder will let us measure very accurately to one place past the decimal, 21.3 or 21.4. But since the bottom of our meniscus falls in between those two measurement markings, we can estimate that second place past the decimal and say, oh, this may be 21.35. Or it may be, you might think it's closer to the 21.4. Again, this is 21.3, this is 21.4. You have to read it from top to bottom. And so if you think it's closer to the 0.4, you might say, oh, this is 21.37 or this is 21.38. Again, it just depends upon, your estimation. Again, it is an estimation there. So when we are doing this, basically, we are going to have our unknown solution. And what we mean by unknown solution is our solution of unknown concentration in the Erlenmeyer flask. Remember that we use an Erlenmeyer flask because it helps to prevent splashing. Because when we're doing this, we're going to be swirling. As we add this known to the unknown, we're going to be swirling the liquid in the flask around. And if we were in a regular beaker, it would be much more likely that we would splash some of that out. And if you did that, you'd have to start all over again. But since the opening to this Erlenmeyer flask is very small, it's easy for us to swirl it around and not really have to worry too much about splashing anything out of it. So anyway, in our flask here, we would have in our own lab, if we had got to do this lab, we would have a hydrochloric acid of unknown concentration in our Erlenmeyer flask, and then so we call that our unknown solution. And then in our burette, we would have our known solution. What we mean there is our solution that has a known concentration, and this would have been NaOH or sodium hydroxide if we had done this lab ourselves. Now, in the video you watched, the unknown solution was an acid in this flask, but it was acetic acid or vinegar. But the known solution was a known solution of sodium hydroxide. So it was sodium hydroxide with a known concentration. And then, of course, we have a piece of white paper here under the flask. The reason for this is because we're going to be looking for a color change. Remember that before you start your titration, before you start delivering known base into your unknown acid solution, you have to add a few drops, 2 to 4 drops of an acid-base indicator. The indicator that we would have used is the same one that she used in the video, phenolphthalein. Phenolphthalein in an acid is clear, but as it becomes more basic, when it becomes basic, it turns pink. Okay, so we're looking for a color change. As we add this known base to our unknown acid, what we're doing is we're bringing the pH of this acid up close to neutral. And the more we bring it up closer to neutral, it will turn pink. So as we drop this base into our acid, we're going to see pink appear, but as we swirl the acid, that pink will go away. Again, we're using 2 hands to do this. One hand is swirling the acid in the flask, the other one is turning the stopcock on the burette to open it up to let the base come into the flask. So as we open the stopcock and let the base flow into the flask of acid, we're going to see pink, but as we swirl it, that pink will go away. We have reached the end point, which basically the end point is when the titration is over. It is when we see the color change, and it tells us that our equivalents of acid and base are approximately the same. We pick up an acid-base indicator whose endpoint is very close to our equivalent point for our acid and base, which basically means the number of equivalents or hydrogen ions of acid and the number of equivalents or hydroxide ions for the base are pretty much the same. So when we see that acid-base indicator change color, we know it's the end of our titration. We have seen the color change. It tells us that we have reached the end point and the equivalence point, which is basically where the equivalents of acid and base are the same. And so for phenolphthalein, again, it's clear, but then when we reach that end point, it turns a pale pink. If it turns a very bright, vivid pink color, you know you have gone too far. Basically what that means is you have overshot the end point, which means you've added more base than you should have. This solution now is very basic, and that's why it's such a bright pink. What you want to see is a very pale pink color. That tells you that you have reached the end point, that you are about there at neutral at your equivalence point. And again, that's why we use the white paper, because this is going to be a very pale pink color, and it will be hard to see up against a dark background. But up against a white background, it's going to be a lot easier to see that very pale pink color. So what we see here then is a little table that we could use to record our data. Again, notice we have the final reading, and this is of the burette, over the initial reading of the burette. The initial reading is the reading that you take before you begin. So once you have your phenolphthalein indicator in your flask of unknown acid and you have your sodium hydroxide in your burette, again, you want this burette, you want the level of liquid to be below 0 so you can read it. You're going to do an initial reading before you ever put any drops of the base into your acid in the flask. You do an initial reading and you write it here. Then, once you're finished, you keep adding that base into this flask of acid until you get that pale pink color change, a pale pink color that does not go away even with swirling. Then you stop. You've reached your endpoint. You stop and you do a final reading of your burette. So whatever the level of the base is in the burette now that we have reached the endpoint, and you would write it here. And then what we're going to do to get the amount of titrant, in this case sodium hydroxide, our base. It's your titrant is your solution with your known concentration. It's in your burette. To get the amount that you use, you take the final reading minus the initial reading. So if our initial reading was 21.35 and our final reading is, let's say that it is 43.35, then we're going to have 43.35 here. We're going to have 21.35 here, and we're going to subtract the 2. 43.35 minus 21.35. Oh, we used 22 milliliters of our sodium hydroxide. And again, the final reading is going to be higher than the initial reading because remember, it starts at 0 at the top and comes down. So as you add more base to your flask, you're going to go from this lower reading up here to a higher reading down here. So again, your final reading is always going to be a bigger number than your initial reading. So we do our final minus our initial to tell us the exact amount of sodium hydroxide or the amount of our titrant that we used. Okay, so I hope that makes sense. I wanted to explain that to you. She didn't really talk a lot about the calculations in the video. She showed you how to do the titration, but the calculations they were doing in the video, they were doing the percent by mass of vinegar, and that's not what we're doing. We're not doing percent by mass, we're doing molarity. So anyway, and if you can hear my son hollering in the background, he's playing a video game with his buddies. So just ignore that. So anyway, what I wanted us to look at now are this would be some data that we might take during a titration. Okay, first we have the volume of our unknown. This is our unknown solution here, our unknown hydrochloric acid that is in our flask. So again, in our flask we have unknown solution of hydrochloric acid. We don't know the concentration of it. That's what we're trying to determine. And so, but we do know how much we used. We put 15.2 milliliters of hydrochloric acid in our Erlenmeyer flask. Then we filled our burette up so that the level of liquid in our burette came up here almost to the 0 at the very top. We filled it up to the 3.55 milliliter mark. Then we delivered sodium hydroxide into our hydrochloric acid until we got the pale pink color change. And the final reading of that burette is 25.25 milliliters. So then what we do is we subtract these two, final minus initial, and that gives us the volume of NaOH, which is our titrant that we used. We also know, remember, this is our known sodium hydroxide solution. We know the concentration of that sodium hydroxide solution, and its concentration, we use the same one every time, so its concentration is 0.500 molar. So again, this is molarity here, by the way, and we can go ahead and put that here. And then our question is, we want to determine the molarity of our acid. So again, the first thing that we need to do, and I don't know where my, hold on just a minute. Let me do this again. Okay, I don't know why it disappeared, but I'm bringing it back up again. Hopefully I am. Okay, there we go. I don't know why it does that sometimes, but anyway. So the first thing we need to do then is we need to calculate the initial and final reading. And notice here, guys, I've done 3 trials, but she told you on the video that, 2 trials are probably going to be sufficient, but if for some reason the 2 trials give you very different numbers as far as the amount of titrant that you used, then you might need to go ahead and do a 3rd trial as well. So that's why I have 3 trials here. Normally, when we're doing this for our second 9 weeks test grade, because guys, this is what we would have done for our second 9 weeks test grade. When we're doing this for our second 9 weeks test grade, normally I have you go ahead and do 3 trials, okay? But as she said in the video, you can only do you can do 2 as long as the amount of titrant that you use for both trials is very similar in amount. So we're just going to look at 2 trials here today. So again, to get our volume of titrant used, we're going to do the final burette reading here for trial 1, which is 25.25 minus the initial, which is 3.55. And again, I'm not sure exactly what that is. Again, we're doing final minus initial burette reading here is what we're doing. So I just want to make sure that you know that. And I'm going to go ahead and type this in on my calculator. Make sure it's clear. We're going to do 25.25 minus 3.55. And we get 21.7 milliliters. And again, that is our amount of titrant used. So I'm going to go ahead and type that in right here, 21.7 milliliters. All right, so let's do the same thing for this second trial. 23.15 minus 1.75. Again, final minus initial, and this is 1.75. So going back to my calculator, because I'm too lazy to do this in my head tonight because it's kind of late, 23.15 minus 1.75 equals. And I get 21.4. So I'm going to go ahead and type this in, 21.4. And again, we're just going to do these two trials right now. And notice that our amount of titrant that we used is very similar, guys. We used 21.7, 21.4, so that means we really don't need a third trial. And I'm not going to worry about averages here. The only thing I'm going to worry about is using these average numbers to calculate my molarity of my acid. Okay, so now that we know the volume of acid that we used, we know the volume of base that we used, and we know the molarity of the base, we can determine the molarity of our acid. Again, we're using molarity and volume here, so we're going to do the M1V1 equals M2V2. And you guys, that will work because notice that this HCl has one equivalent and this NaOH also has one equivalent, one H and one OH. So, but because they both have one equivalent, we can use molarity. If we were using HCl with one equivalent and H2SO4 with two equivalents, then because it has two hydrogen ions, it would have, or I'm sorry, let's say we were using HCl with one equivalent and CaOH2 with two equivalents, two OHs, then we would want to go ahead and use normality rather than molarity. We could take these molarities and convert them to normalities using those equivalents. But since these both have one equivalent, it's fine just to use MV equals MV. And again, this is, instead of using M1V1 and M2V2 here, you could actually use, it's the same equation, but you can say molarity of the acid times the volume of the acid is equal to the molarity of the base times the volume of the base. Okay, so again, you got acid and base. So, I mean, it's the same equation that we were using in the dilution problems. The only difference here is we're doing a titration. So instead of having solution 1 and solution 2, which you could still say you have, we have an acid and a base. So this makes it a little bit more clear. Okay, let's take the molarity and volume of the acid equal to the molarity and volume of the base. Again, because both HCl and NaOH have one equivalent, molarity works fine. If one of them had one equivalent and the other one, like CaOH2, had two equivalents, then we would want to convert both molarities to normalities and do NaVa equals NbVb. But on your test, I'm also going to give you HCl and NaOH. So you can go ahead and use the MaVa equals MbVb. Okay, now remember, we're calculating the molarity of the acid. So right away we know that Ma is our X. Volume of acid. Well, how much acid did we use? Well, right here, we used 15.2 milliliters of acid. Okay, and then the molarity of our base, we do know this is our base. It's 0.500 molar. And how much base did we use? Well, the volume of base that we used was 21.7 milliliters. Again, I'm just doing this calculation for our trial 1 first. So again, to solve this, we're going to have to divide both sides by 15.2 milliliters. This cancels out. Milliliters cancels out over here. And we have X is equal to 0.500 times 21.7 divided by 15.2. So let's type this in our calculator. So 0.500 times 21 point, oh, let me try this again. 0.500 times 21.7 equals, and then divided by 15.2. Divided by 15.2 equals. And I get 0.714, and it looks like that's what I'm going to use as far as my significant digits go. Let's see. Yeah, I think that's going to be fine. So we got 0.714 molar. Okay, so that is going to be our molarity for trial 1 for our acid. So HCl molarity trial 1 is equal to 0.714, okay, molar. Now we're going to do the same thing, but we're going to do for trial 2. Okay, so let's go ahead And get ready to do trial 2. So first of all, we've already got our thing here. We just need to do our calculation. So again, we're going to do MAVA equals MBVB. Again, we know we want to calculate the molarity of our acid, so that's our unknown. In trial 2, the volume of acid that we used was 15.1 milliliters, so 15.1 milliliters. The molarity of our base, again, is the same, 0.500 molar. And the volume of base that we used in this trial was 21.4 milliliters. Again, to solve for our x, we're going to divide this time both sides by 15.1 milliliters. 15.1 milliliters cancels out, milliliters cancels out, and we're going to do 0.500 times 21.4 divided by 15.1 on our calculator. So clear everything. 0.500 times 21.4 equals divided by 15.1. 15.1 equals. Again, we need 3 significant digits here. It looks like it's going to be 0.7086 rounds to 0.709. So our answer here is 0.709 molar. So that is for trial 2. So 0.709 molar. Now, before I do a percent error, you guys, what I'm going to do is I'm going to calculate an average. An average molarity. So what I'm going to do is I'm going to take the 0.714 plus, to get my average, my 0.714 molar plus the 0.709 molar divided by 2. And that will give me, from these two trials, the average HCl molarity. So, go back to my calculator one more time. So 0.714 plus 0.709 equals, divided by 2 equals. And then I want to round that to 2 significant digits, so 0.7115, I would round to 0.712, so 0.712 molar. And so that's what I'm going to put in here, 0.712 molar. And again, on your test, you're going to have a problem very similar to this. It's just going to have 2 trials. You're going to do very similar to what I'm doing here. You know, don't just show me this that I've written here, but, you know, show me this work. Show me all this work that you've done. Again, all this work that we've done here. You know, where we've done the final minus the initial, where we've done the MAVA equals MBVB for each trial, and then where we've done the average. So make sure you show me that information. Okay, so now that we've done that, the last thing that we need to do is calculate our percent error. And if you remember, percent error, and I give you this equation on the test as well, is equal to the actual minus the experimental. Again, you're going to do the absolute value there. Divided by the actual, and then times 100. So again, if the actual molarity of HCl were 1.00, calculate percent error. So the actual is 1.00 minus our experimental, which up here what we calculated is our experimental, so 0.712, divided by the actual, which is 1.00, times 100. Okay, so let's go back to our calculator one more time, and I'm sorry, here it is. The actual is 1.00, it told us this in the problem, minus 0.712, that's our experimental, that's what we calculated, divided by the actual, which is 1.00, times 100. Now we're going to punch that in our calculator. So let's clear it first, don't forget to clear it. 1.00 minus 0.712 equals, divided by 1.00 equals, and then times 100 equals. And our percent error is 28.8%. So that is not great for this. So what we got here is 28.8%. So again, if this were you doing this for your lab, for your second-nomics test grade, if you get 10% error or less, then you would have gotten 100. If you got like a 20% error or less, you would have probably gotten in the 90s. If you've gotten If you'd gotten, that's 10%, between 10 and 20% error. If you got between 20 and 30% error, you would have probably gotten in the 80s. So this would be an 80 something that I would have given you probably for this amount of error. Now in college, when you get to junior, senior chemistry classes in college, if you get more than 10% error, you get a 0 and you have to redo the whole entire 5-hour lab again. So, but they have a lot better equipment. Like you saw in the video, she talked about writing the mass down to 3 places past the decimal. Okay, I don't even have a balance that will measure 2 places past the decimal, much less 3. So therefore, I don't expect you guys to get really, really like 1% error or less. So in the high school classroom, because our equipment just isn't as accurate as what it could be, because we can't afford that really expensive equipment like they can at the university. If my students get 10% error or less, I'm like, yeah, man, you deserve 100 kind of thing. So this would probably be an 80 something if you had done this in lab for me. So this isn't great, but it's not terrible either, but could be much, much better. I just want you to realize that. All right, so this is the kind of titration calculation that I want you to be able to do for me on the test. You know, you're going to have a data table that looks very similar to this, just with different numbers. You're going to have to calculate the volume of titrant used. You're going to have to be able to calculate the molarity of the unknown acid for each trial 1 and 2, and then get me an average molarity of the acid and calculate the percent error just like we did here. So please let me know if you have any questions. I will be happy to help you. Again, we can FaceTime, we can Skype, something like that, and I can go over anything that you need me to go over with you. Otherwise, I know this has kind of been a long video. I hope you have a great day and rest of your week. Good luck on your exam, and I'll be talking to you later. Bye-bye.